Welcome everyone. In this video I have an interesting question that I want to ask you guys. So if we have an inclined plane like this one and we have a block that just entered the inclined plane and our block has an initial velocity of v0 which is along the inclination. So, as you can picture this in your head, and probably you encountered this in real life, this block is going to travel to some distance, maybe to this point, and as time will pass, right? Maybe we call it t up. So it starts with v0 and it comes to a rest, and the time between those two is t up. We define it like that. And then, of course, our block will now start to fall in the opposite direction. And we are interested in the point where it comes to its initial starting position. So back to this point. And we call this time, the time that it takes for that motion to happen, t down. Now, my question to you is, which one is greater, t up or t down, or are they equal? And provided, very importantly, there is friction. So this is not a frictionless inclined plane. This is a problem where we have friction. So there is friction. I mean, you may want to stop the video and think about it a little for a couple of minutes if you want. And if you're ready, let's get started. So as I said, the question is, how can we compare t up and t down? And to make our comparison, we will use an equation that I derived in the last video. Specifically, the last kinematics equation that we derived. And that was, for delta x, it said that it was v average times time, and it was equal to v0 plus the final velocity divided by 2 times time. So we are going to use this one. And in the last video, if you watched it, you know that I said that I don't really like this equation. I didn't used to like it in the past. I found it unnecessary. Well, this question, I really mean it. This question was the point where I realized how effective this formula can be. Because there are other solutions to this question, but this way that I'm going to show you, using this equation, is the easiest way of solving this question, at least the one I know of. So, we're going to now be interested in the upward motion. So, for up, let's say that we travel for a distance of L. Alright, and of course, our coordinate plane is like this. X is along the inclination and Y is just perpendicular to the inclined plane. So we travel a distance of L, and oh, it looks like P maybe. So L. Well, L is going to be equal to, using the formula, our initial velocity, which I call v0, plus our final velocity. Well, our final velocity is, drum roll please. Yep, you guessed it correctly. It is 0. We just come to a stop. It is 0. Divided by 2 times t, and specifically t up. So we get, if we solve for t up here, t up is going to turn out to be, well, it will be 2L divided by v0, right? So this is the upward motion, and we found a formula for t up. Now let's consider the downward motion and try to find a formula for t down this time. So we have the down. Well, if we think of the downward motion, and I want to draw our inclined plane here one more time so that we will be able to picture it. We start at this point where we come to rest, where our upward motion ended. We just come to a momentarily stop, and then we start our downward motion. So at the beginning, we will have a velocity of 0. Then we accelerate due to gravity, and then we come to our initial starting position, the point where we had a velocity of v0. So, I mean, we should have v0 again, right, by the conservation of energy? No, we won't have v0, because for energy to be conserved, we need to account for the energy that was lost to friction. As I said, there is friction. So while we moved up and down on this inclined plane, there was some energy lost to friction. It might be in the form of heat, and it probably is mostly in the form of heat. But in any case, it was lost. Some energy was lost to friction. So our velocity here, which I will call v, should be less than v naught. I mean, I hope this makes sense, right? You lose some of your energy to friction, so when you come back to your starting position, you now have less kinetic energy, so less velocity. Well, since we got that out of the way, now let's write the equation for the downward motion. We will have negative L. Why did I write negative? Well, because we are traveling in the negative direction according to our coordinate plane, since we set it like this. This is going to be equal to our initial velocity, in this case was 0, plus we will have some v value, and it is in the negative direction, so we put a negative v. We divide by 2 and we have t, specifically t down. So if we solve for t down now, we get that t down is equal to 2L divided by the velocity we have. All right? So this is all great, and we are at a point where we are really close to the end of the question now. So if we look at these formulas, one for t up and one for t down, well, you see that we have 2 and L, those are constants, and we have division. The only difference is V naught and V. So we said that V naught is greater than V, which means that here, for the T up formula, we are dividing by a greater number, right? So a greater number is in the denominator, which means that T up is going to be less. T up decreases, right? Due to a great velocity, you have less time. And if you look at here, you have a small velocity. You divide by a small number, so you get a greater value here. So T down is going to take longer, which means going up motion is taking longer than going down motion. So let's take it. I think I said it wrong again, but I don't know. So the result is T down is greater than T up. It takes more time for our block to travel downward than it takes for it to travel upward. The upward motion takes less time than the downward motion. I hope this calculation makes sense and shows you how useful this delta x formula that we derived in the last video can be. Anyways, if you have any questions or suggestions, please write them in the comment section. I hope to see you in another video. Until then, take care.